Now we'll be talking about limit of a function. So what do we mean by the limit of a function and how do we find it? So now before we go into that, let's quickly take a look at what we mean by a function. So a function assigns a single output value for each of their inputs. So what do we mean by this? So think of a function like a machine. So we have a machine over here in which we are told that y is equals to 3x plus 1. So what this machine does is that for any value of x, we can figure out the corresponding value of y. For example, let's assume that the value of x is equals to 0. So now we know that y will be equals to, we just substitute the value of x as 0 into this engine here. So we have 3 into bracket 0 plus 1. And we know that 3 times 0 is 0, then plus 1 will give us 1. So when x is 0, this function works out the value of y to be 1. How about when x is say equals to 3? So we substitute it into our engine. So we have y will be equals to 3 into bracket 3 plus 1. Now we know that 3 times 3 is 9. So we have 9 plus 1 and that gives us 10. So when x is 3, the value of y is 10. Now let's take a look at this other example over here. And here we are told that f of x is equals to x squared plus 3x plus 5. So I should quickly mention that anytime you say f of x, is the same thing as having y. So what we mean by here is that f is a function of x and this defines the function of the engine. So the same logic applies. If x equals to 0, for instance, we can find the value of f of x by substituting the value of x into the function of the engine. Yes, we have 0 squared plus 3 into bracket 0 plus 5, and that gives me 5. So f of x is 5 when x is 0. How about a case when x is equals to 1? So I have my f of x being equals to 1 squared plus 3 into bracket 1 plus 5, and that gives me 1 plus 3 plus 5, and that gives me what? 9. So as you can see, this is the way a function works. For any value of x, we can find the corresponding value of y. So what does it now mean to find the limit of a function? The limit of a function is a mathematical concept in calculus and analysis concerning the behavior of that function near a particular input. So what I mean by this is that now let's assume the value of x tends or gets closer to a particular number. How does the function or how does the variable y behaves? So that is what the limit of a function entails. So now let's take a look at this function over here. And in this function, we are told that y is equals to x raised power minus 3. So I can write it out also as, if you remember your law of indices, x to the power of minus 3 is same thing as 1 over x raised to power 3. So I ask that what happens as x approaches infinity. So now as the value of x changes and gets closer to infinity, what happens to the value of y? So that is what we mean by the limits of this function as x tends to infinity. So to get started, let's assume that x is equals to 10. So if x is equals to 10, I can find the value of y, which will be equals to what? 1 over 10 cube. If I substitute the value of x here, so I have 1 over 1000, which is equals to 0.001. Now if x is equals to 100, my y value will be equals to what? 1 over 100 cube, and that will be 1 over 1 million. And when you punch this into your calculator, you have 0.000001. So now let's assume x now tends to infinity. This is the symbol for infinity, and infinity also means a very large number. So I have 1 over infinity cube. So now think of 1 over a number that is very large, very, very large, which is infinity. What would that value be equal to? As you can see, the value is decreasing as x is increasing. So when the value becomes very large, the value of y tends to be equal to what? 0. So the way we write it is that what? We say that the limit of x raised power minus 3 as x tends to infinity is equals to what? 0. Meaning that as the value of x gets very large, larger and larger, then this function gets closer to 0. So how do we find the limit of a function? So there are 3 basic steps to finding the limit depending on the difficulty level of the question. So let's start from the first level. So here we are told that first you put in the limiting value into the expression. If the result is defined, you have the limit. Very straightforward. So now, for instance, we are told to find the limit of the function y is equals to 3x as x tends to 2. So the way we write that down is that write that the limit of the function 3x as what? As x tends to 2. So it tells us that what do? We just substitute the value of x directly into this function here. So when we substitute it into this function, what do I have? I have 3 into bracket 2, and that gives me 6. Now 6 is defined. What does it mean for a number to be defined? It means that it is a reasonable number, a number that can be expressed on the number line and is reasonable, like 1, 2, 3, 4, 5, minus 1 and so on. So this is a definite number and is defined. So we stop at this step. So the limit of this function 3x as x tends to 2 is equals to 6. Now let's take a look at more examples. So in this first example, we are told to find the limit of this expression as x tends to 0. So again, what do? I just substitute the value of x as 0 into the expression. So I have 0 squared plus 5 into bracket 0 plus 9 over 2 times 0 squared minus 3 times 0 plus 15. This is 0, 0 and this becomes 9. This is 0, 0 and this becomes 15. So that becomes what? 3 over 5. As you can see, 3 over 5 is a defined number. So the limit of this function as x tends to 0 is 3 over 5. Now let's take a look at another example. I was told to find the limit of this function as x tends to 0. So I substitute x as 0 into this expression. So what does that give me? So that becomes 7 minus 2 into bracket 0 plus 5 times 0 squared minus 4 times 0 cubed. And this becomes 7 plus, all this terminates to 0, minus 0 plus 0 minus 0, and that is equals to 7. Again, 7 is a defined and definite number. So the limit of this function as x tends to 0 is 7. Now, there are some special cases in which when we substitute the value of x into the expression, the result we get is undefined. So what if the function is undefined? How do we deal with it? So what we'll do is that we'll try to see if factorization can help with the simplification. Now, to illustrate that, let's take a look at this example. I thought to find the limit of this function as x tends to 5. So based on our first step, what we have to do is substitute the value of 5. So this becomes what? 5 squared minus 25 over 5 minus 5. And that becomes what? 25 minus 5 minus 25 over 0. And that becomes 0 over 0. Now, I want you to briefly take your calculator and I want you to punch in the value 0 over 0. Now, when you do that, or if you have done that, you find out that your calculator is going to give you an error message, either math error or undefined. So what it means is that there is no definite value in which you can assign 0 over 0. So now, to generalize this idea, when you have a number in which the denominator is 0, it will always give you an undefined number. For example, take your calculator again and punch in 7 over 0. You get an undefined number. Try 10 over 0, you get an undefined. Insofar as the denominator is 0, you always get an undefined number. However, if the numerator is 0 and the denominator is not 0, you get a defined number which is equal to 0, like 0 over 5. I know it's 0. 0 over minus 10, I know is 0. So to recap, anytime you have the denominator, anytime you substitute the value of x and the denominator works out to be 0, then know that you cannot substitute directly. So we'll try to see if factorization can bail us out. So let's apply factorization. So now we can try to factorize this numerator. So now we are trying to evaluate the limit of x squared minus 25 over x minus 5 as x tends towards 5. So I can try to factorize this numerator, and to do that, if you recall from our difference of two squared discussion, we mentioned that x squared minus 25 can be written as 5 squared, can be written as what? X minus 5 and what? X plus 5. So that is from our discussion on difference of two squared, where we told that if you have a squared minus b squared, is the same thing as a plus b times what? A minus b. So that is pretty much what we have applied here. So now I can substitute here. So this becomes what? The limit of what? The limit of the numerator becomes x minus 5, x plus 5 over x minus 5. I find the limit of x as x tends towards 5. Now I can see that x minus 5 cancels out x minus 5, and I'm left with the limit of x plus 5 as x tends to 5. Now when I substitute this value into this expression here, I get a definite result, a defined result. So if I substitute the value of x as 5, I have 5 plus 5, and that gives me what? That gives me 10. So the limit of this function as x tends towards 5 is what? Is equals to 10. So you should take note, when you try to solve it directly, if the denominator works out to be 0, you try to see if factorization can work out. Now let's look at some more examples. So now I'm trying to find the limit of this function as x tends towards 2. So first and foremost, the first thing you want to do is you want to see if the function is defined or not. And to do that, we substitute the value of 2 into the denominator. And when we do that, we have what? 2 squared minus 2 into bracket 2. And that gives us what? 4 minus 4, which is equal to 0. So when I substitute this into this expression here, my denominator is going to be 0. So this function is undefined. So what do I have to do? I have to check out if I can try to factorize these terms. And luckily for us, it is possible to factorize. So we'll start about factorizing the numerator. So we have what? The numerator. So we have what? X squared plus 4x minus 12. So we'll multiply the first and the last term. That gives us minus 12x squared. Then we'll ask ourselves what two numbers can we multiply together to get minus 12x squared. But when we add them together, we get 4x. And those numbers turn out to be what? To be 6x and minus 2x. Because 6x times minus 2x gives us minus 12x squared, and 6x plus minus 2x gives us 4x. So we replace 4x with this, and that becomes x squared plus 6x minus 2x minus 12. Now x is common here, and I have what? X plus 6, and minus 2 is common. I'm left with x plus 6. So I pick one of these, which is what? X plus 6, and I put the remaining in bracket, which is what? X minus 2. So when I factorize the numerator, this is what I get. So how about when I factorize the denominator? So the denominator is pretty straightforward. So for the denominator, I have x squared minus 2x. I see that x is common, so I factor that out, and I'm left with what? X minus 2. So now that I've factorized the numerator and denominator, I can now substitute it here. So this expression I can rewrite as what? The limit of the numerator becomes x plus 6 x minus 2 over the numerator becomes x into bracket x minus 2 as x tends towards 2. Now as you can see, x minus 2 cancels x minus 2, and I'm left with the limit of x plus 6 over x as x tends to 2. Now I can substitute the value of 2 here without having the denominator as 0. So this becomes what? 2 plus 6 over 2, and that becomes 8 over 2, and that results in what? 8 divided by 2 is what? Is 4. So the limit of this function as x tends to 2 is equals to 4. So to recap, what we did first was we tried to substitute the value of x to the denominator, and we got the denominator to be 0, so we know that it was undefined. So we tried to factorize and simplify before we worked out and substitute the value of x as 2, which we eventually got to be 4. Now there is one more special case. If factorization fails, what then? So if we try to put in the value into the function and we get the denominator to be 0, we try to factorize it, but we can't factorize it because of the nature of the expression, then what do we do? Then what we do is that we'll make use of the L'Hopital's rule. So the L'Hopital's rule is based on differentiation, and what it says is that the limit of f of x over g of x, where f of x represents the numerator and g of x represents the function of the denominator, as x tends to a is equal to the limit of differentiation of f of x. This f prime of x means the differentiation of this function, and this g prime of x means the differentiation of this function as the limit x tends to a. So to give you an example, let's try to solve this example over here, where we are told that we should find the limit of this function over here. So now we see that if we put the value of x as 0 into this function, I have what? 0 cube plus 5 over 0, which becomes what? 5 over 0. As I can see, the denominator is 0, and when you punch that to your calculator, you get an error message. So this function is undefined. So now I'll try to see if I can factorize, but there's no way that I can factorize the numerator. So what do? I apply the L'Hopital's rule. So this expression can also be written as the limit as x tends to 0. Now I try to differentiate the numerator. Now I have not talked about differentiation. I will talk about it in the next module, so I'm just going to walk through it now. So when I differentiate this numerator, x cubed becomes 3x squared and 5 becomes 0. And when I differentiate x, the denominator, I get 1. So now I can fix the value of x as 0 now into this expression. So I have what? 3 into bracket 0, and that is equals to 0. So the limit of this function as x tends to 0 is equals to 0. So to recap, what we did was we first substituted x as 0 into this function, and the denominator worked out to be 0, which made the function undefined. So we had to factorize, but in this case we could not factorize. Then we were left with no choice than to apply the L'Hopital's rule, which tells us to differentiate the numerator and denominator before we apply the limit. So when we differentiate the numerator, we got 3x squared, which I will explain in the next section. And when we differentiate the numerator, we got what? 1. So when we substitute x as 0 now, we got the limit to be equal to 0. So now what is another use of the L'Hopital's rule? So we are going to be looking at the questions that we solved before, in which we use the factorization method. So for this first example, when we found the limit, what did we get? We got the limit in this case to be equals to what? To be equals to 10. But now let's try to apply the L'Hopital's rule to see if we get the same thing. So applying the L'Hopital's rule, we differentiate the numerator and the denominator before we apply the limit sign. So the limit of x tends to 5. So we'll find it and we differentiate the numerator. When we differentiate the numerator, x squared becomes 2x. This becomes 0. Then over x becomes 1. So when we differentiate this expression, the numerator, we get 2x. And when we differentiate the denominator, we get 1. So now if you apply x as 5 now, so this becomes what? 2 into bracket 5, and that is equals to 10. As you can see, we got the same answer like we did when we used factorization. Now in the second example we solved, we worked out the limit to be equals to 4, and we used factorization. So let's see if the L'Hopital's rule can also be used. So applying the L'Hopital's rule, we have to differentiate the numerator, and when we differentiate x squared we get 2x. When we differentiate 4x we get 4, and this becomes 0. Then over, when we differentiate x squared we have 2x, and when we differentiate minus 2x we get minus 2. So now we can substitute the value of x as 2. So that becomes what? 2 into bracket 2 plus 4 over 2 into bracket 2 minus 2. And that becomes 4 plus 4 over 4 minus 2, which works out to be 8 over 2, and that results to 4. So as you can see, we got the same result of this function tending towards 4 as x tends to 2, this function tends towards what? 4. So as you can see, this pretty much sums up how we deal with finding the limit of a function. And I know that for some of you, how we differentiated the numerator and denominator might look strange, but now we're going to be looking at differentiation proper, and when we do that you will see how I differentiated the numerator and denominator, and you'll find out that it is really easy to do. So let's look at differentiation of algebraic expression and trigonometric functions now.